Hi everyone, I'm Professor Bergasser, and in this video we're going to be computing some moments of inertia for some commonly shaped objects. Now remember that a moment of inertia is this distribution of mass, the sort of shape of an object that we need to know in order to convert between an applied torque and the resulting angular acceleration that comes out of that applied torque. It has the equivalent meaning of mass when we're looking at Newtonian mechanics, where force equals mass times acceleration. The greater the mass, the less acceleration you get out of the same force. So it's kind of a resistance to motion. In the same way, the moment of inertia is a resistance to rotational motion. The larger that moment of inertia, the smaller the resulting angular acceleration is for a given applied torque. Now the moment of inertia is just one of our moments of mass, which is really just mass times a coordinate axis. The most simple moment of mass is just the total mass, where we break up our object into lots of little pieces, add up all of the masses across that object, and we get the total mass of our system. All right, we've looked at that many times before. We've also seen the center of mass, which is a vector quantity, and that's just adding up all of the little mass elements times their position within the object, and then dividing by the total mass of the object. So this is kind of a mass-weighted position inside the object, and it literally gives our center of mass. And this is where, of course, many of the body-centered forces like gravity or weight act on when we're looking at an object in motion. That's the first sort of moment. The second moment is our moment of inertia, and that's just adding up those little pieces of mass but multiplying by the radius squared, where this radius is the distance, and of course is a distance squared, perpendicular to our rotation axis. Okay, so we're going to use that definition in this video to see if we can calculate what the total moments of inertia are for some very simple objects. And of course, because it's an additive expression, as we build up more complicated pieces, we can measure the moments of inertia of many things together by taking our expressions and combining them. Now, this is true for any origin of any coordinate system we're looking at. We can decide to set our origin wherever we want and compute a moment of inertia for our object about an axis that goes through that origin. But we can also define a rotation about the center of mass, or a moment of inertia about the center of mass, where the rotation axis passes through that center of mass. And that's just setting the RIs as relative to our center of mass coordinate. All right? So that's just choosing our origin to be at the center of mass. Now, if we decide on an axis that's separated from the center of mass, if we don't want to rotate this pen about its center of mass but about one end, then that can be computed from our parallel axis theorem as the sum of our center of mass, our moment of inertia about the center of mass times ml squared, where this is the perpendicular distance to a parallel rotation axis. Okay, so these expressions will be very useful for generalizing our moments of inertia for basic shapes and computing what an object would look like if it's rotating, again, at a distance or with a more complicated shape attached to it. Now, we've already seen some simple moments of inertia. All right, we've had some examples of looking at just the case of a mass on a string, a massless string of some length r and mass m. All right, this is kind of the point particle example, and the moment of inertia we calculate for that is simply mass times radius squared. Again, this is the rotation axis right here. We've also looked at a generalization of that where we took a hoop, right, of radius r, and again, if this is our rotation axis, and I'll set that here as well, which we're measuring, this is really adding up all these little points along this radius rim. And so we can compute that with our definition, sum of delta mi times ir squared, but all of the radii relative to the center of mass are all the same distance, which is just this capital R. So that term comes out, r squared, sum of our little masses, but of course that's just our total mass, so we get mr squared again. which is identical to the moment of inertia of just this point mass that's swinging around by a string. We're going to see that symmetry again later on as we look at some more complicated shapes for moments of inertia. So as our first example, let's take a look at the moment of inertia of a solid disk. So this might be a frisbee or a plate, and we can build on our solutions based on what we've solved before for just the point mass and the hoop or ring. Because when we think about it, the disk itself is really just kind of a composition of lots of little rings as they're building out. So just as we took that point mass and added them up as we go around a circle to make our hoop or ring moment of inertia, we can take our disk and add up a bunch of hoops to build out the shape of our disk. So let's assume we've got a series of little rings or hoops that are passing through our disk here. Then we can calculate the total moment of inertia of our disk as just the sum of, let's rewrite that so it's a little more clear. We can just add up all of the moments of inertia of these little rings as we're going outward from the center. And because this is an additive process, it's a perfectly reasonable way to calculate the moment of inertia of this whole object. So let's take this ring out and actually calculate what its moment of inertia is. So we're starting at some distance Ri from the center. So we're just looking at somewhere between the center and the full radius r. We've already calculated the moment of inertia of a ring as just the mass contained in that ring times Ri squared. But what is this mass? How much mass is contained in this little ring? Well, this, if we assume, and we're going to assume this for the rest of the shapes, so here it is that these things are even density, they're constant density, there's no little high mass or low mass points inside of them, then we can compute this as the areal density, all right, the mass divided by the area of the disk, times the area covered by this little piece of hoop. So the areal density is just the total mass divided by pi times the big radius squared. And the mass, the area of this hoop, well, this is a circle, right, that has a finite width. We'll call this delta r. And so the area is just really just the length of this line times its thickness. And the length of that line is 2 pi times Ri, and then times its thickness delta r. And so this gives us, we can cancel out the pi's, so this gives us 2 m over r squared times Ri and then cubed delta r, all right, because we've got 1 Ri from our mass term and 2 Ri's from our radius term, our distance squared term. Okay, so if we're calculating the moment of inertia of our disk, we're just going to sum up all of these moments of inertia of rings. We can carry out our constant values from our summation, and we're left with this sum of Ri cubed times the little bits of widths that we're adding up as we're moving out from the center of the disk to the edges. Now, anytime you see a continuous medium example like this where we're adding up little pieces, we can turn this summation into an integral where we're integrating from the origin out to the radius of the disk times the radius cubed dr. So that's the integral form of our summation of little pieces. And this is a fairly simple integral to do. It's just equal to 1/4 times r to the 4th. So if we go back to our measure for our I disk, it's going to be 2m over r squared times 1/4 r to the 4th, and that gives us 1/2 mr squared as our final answer. Now, it's worth at this point to think a little bit about this solution. We've got a full disk here that's 1/2 the moment of inertia of a hoop of the same size and same mass. And if we think about it, that should make sense because what we're really talking about in terms of resistance for rotational motion, we've got all of our mass on the outside of our shape. That's going to be a lot harder to turn with the same amount of torque than if we distribute that mass more evenly and in particular bring more of it closer to the rotation axis. So we should have expected to have a smaller moment of inertia for our disk, and that's exactly what we got. And that factor between going from all the mass to the edge to distributing the mass evenly throughout the shape is just introduces a factor of 1/2 in our moment of inertia. Now let's generalize our expression for our moment of inertia of a disk to a three-dimensional equivalent object, and that's a solid cylinder illustrated here. So again, let's look at the case where the cylinder is uniform distribution of mass, and it's rotating about an axis that goes along its long axis through the cylinder. We can approach this problem much the same way we did in the last one. We know what the moment of inertia of a disk is, a two-dimensional disk. A cylinder is really just adding up all those two-dimensional disks along the axis, along the rotation axis, until we've covered the entire volume of the cylinder. So again, we can write this down as the cylinder is equal to the sum of a bunch of moments of inertia, which are all values for the disk, all right? And each of those disks is going to be 1/2 times the mass contained in that disk times the radius, which is just r squared. And then we're going to be adding up these masses along the length of the path. But notice that we have 1/2 r squared, which is constant, times the sum of our little masses. And we actually already know what that number is. It's just the total mass. So it's going to be 1/2 times the mass times radius squared. And that's it. That's the answer for our cylinder. We actually didn't have to even worry about the length of the cylinder in order to calculate this. Now, this is generally true whenever you have a shape that extends uniformly along the rotation axis. That shape has the same moment of inertia as the 2D plate or cross-section that is perpendicular to the rotation axis. Okay, so this is true for our cylinder. If I wanted to do an extremely thin pipe, just like a long sort of tube, that would just be extrapolating our ring measurement out backwards, and we would get still the same exact moment of inertia. So as long as the mass distribution doesn't change as we go down the length, you're still going to get the same moment of inertia for this three-dimensional shape. And that makes it much easier to calculate some of these things. Now, another case we can consider is a hollow cylinder. And this might include, again, a pipe, or maybe includes a tire if it's not that thick in the z direction. That would be the case of a tire or a donut or a bagel if you want to compute the moment of inertia of those. And in those cases, what we're really looking at is not a summation, but really a difference. So if we have our hollow cylinder that looks like this, with an inner edge and an outer edge, we'll call that capital R and little r. In fact, this shape is really the difference between a full cylinder, or a full disk, minus a small cylinder or disk. We're literally taking that mass out of the center of our cylinder or disk. And again, because this is just an additive process, you can subtract just as much as you want to add. And so this is a perfectly reasonable way of figuring out what the moment of inertia of this hollow cylinder is. But again, we know what the moment of inertias of these two pieces are. This is going to be 1/2 times the mass times the full radius squared, and this is 1/2 times the mass contained in there times that radius squared. And when you combine all these things together, you're going to get a total moment of inertia of 1/2 times the mass times the difference between these two radii. All right, so it's very powerful to use the sort of additive and subtractive methods for these moments of inertia, because once we have, again, a base, we can build up different shapes based on just moving these different pieces around. All right, let's go on to our next shape, which is a shape we're more familiar with when we're talking about rotating things, and that's a sphere, because this could be something like a basketball or a baseball or any kind of ball that we're rotating or spinning around. In this case, we can again build on what we've built before in terms of what is the moment inertia of flat shapes, and then build them up into these three-dimensional shapes. In this case, we're going to use a solid sphere, so what we're looking at is the moment inertia of disks, and then adding up the disks as we go through this three-dimensional object. But in this case, that three-dimensional object disk size changes as we progress through the material. So I've tilted this over on its side, so the rotation axis is really running along this direction, so we're rotating the ball around that axis this way. And we're going to look at adding up, for our moment inertia of a sphere, the sum of moments inertia of slices through the sphere, where each of these slices is a disk, and so we're looking at the moments inertia of different disks. Now let's take just one piece of disk. So if I start here at the center, and I look at taking a slice down through the sphere at some distance z from the center point of our sphere. Remember that this radius here is just the radius of the sphere, which is r. And now we're looking at a disk that has a radius of essentially r times sine theta. If this angle is theta here, that's going to be the radius of our disk there. Or we can use Pythagorean theorem and just write it down as r squared minus z squared, because this makes a nice right triangle. In any case, let's see if we can write down an expression for one of these disks and then add them up as we go through the sphere. Well, we know that the moment inertia of a disk is 1/2 times delta mi times ir squared. In this case, we need to write down an expression for both of these terms. Delta mi is just the mass contained in this one little disk, and that's the mass, total mass of our sphere divided by its volume, which is 4 pi over 3 times r cubed. All right, that's our density. And then we're going to multiply by the volume of our little disk slice. Well, that's just the area of our disk slice, pi times ir squared, times the thickness of it, which is just a little step in our z direction as I've drawn here. And then the ri squared, unlike the cylinder case, is actually going to change as we move away from the center of the sphere. So we need to write down an expression of that. And again, because of the Pythagorean theorem, it's very easy to write this down as ir squared is equal to the hypotenuse of our triangle, which is the radius, minus how far away we are from the center of our sphere, which we've given as a coordinate z. So let's combine these pieces into the moment inertia of our sphere. I'm going to carry out the constant values, which includes the 3/4, because that's 4/3 over itself, times mass over r cubed. And now inside our sum, we've got ri squared squared, so that's 4th power, and we've already written down as r squared minus z squared, so that is that quantity squared, and then times our delta z, which is our step as we're going through the sphere out from one end to the other one. Now, as we did before, because this is a sum over a little piece, we can turn this into an integral. That's going to be the integral of r squared minus z squared squared dz instead of delta z. And in this case, the integral is going to be running from one end to the other one. So if I set z as 0 at the midplane here, I can do it from minus r to r. But notice that whatever I do this way is going to be exactly the same as I get this way. So even simpler, I can multiply this times 2 and just integrate over half of the sphere from the center point out to the radius. All right, so now this just becomes a math problem. It becomes about writing down solving for this integral. Let's do a little bit of this so you can see how these kind of integrals are approached. We can do this as a substitution of variables because it's a little hard to square out this term, but we can substitute in an expression there that will make this much easier to solve. And the expression I'm going to use, I'm going to assume that z is equal to r times sine theta. So I'm going to include my angle term in here to see if I can make this a little more simple. Well, that means that dz is r times cosine theta d theta, just taking the integral of z with respect to theta. And that also means that theta is going to run from where z equals 0, so that's when theta equals 0, to where theta is equal to pi over 2. That's the range for our integral for that expression. So let's rewrite this, and keep in mind that I can take out now in r to the 4th, because I've got r squared squared, I'm going to have an r squared there, and I'm turning this into r cosine theta. So in fact, the total I have is an r to the 5th. So this whole integral is 2r to the 5th times the integral of 1 minus sine squared theta squared times cosine theta d theta over these integration ranges. And now the reason I made the substitution is, of course, we can use our trigonometric relations that sine squared plus cosine squared is equal to 1. That means that 1 minus sine squared is equal to cosine squared theta. So this whole thing turns into 2r to the 5th times the integral from 0 to pi over 2 times cosine to the 5th theta d theta. And this looks like an easier integral to do. In fact, it's still a little more complicated. And normally for these kind of integrals, you want to either look into an integration table, or you can solve this by integrating by parts. But in either case, you can come up with a numerical value for this of 8/15 by doing your integration carefully. That's a nice simple numeric value at the end there. So if I combine all of these terms together, I have is is equal to 3/4 m over r cubed times 2r to the 5th times the number that comes out of my integral, which is 8/15. Combine this all together and you get 2/5 times mr squared. And that's the moment of inertia of our sphere. So clearly this is a little more complicated of a shape to do the moment of inertia from, but the approach is still the same. Looking at our shape into, breaking our shape into pieces of objects that we do know how to calculate the moments of inertia from, and adding those pieces together, in this case adding them in an integral form so that you can get out the actual expression for our moment of inertia of our shape, in this case the sphere. Now we can repeat this again for a hollow sphere by doing the same example we did with our hollow cylinder, just subtracting out a smaller sphere from our wider sphere, and we can get out an expression for that moment of inertia of that object as well. All right, let's do one more example, and we'll do one that's not as spherically symmetric, but also a still useful object to see what the moment of inertia is, and that's the moment of inertia of just a flat, straight stick. So this would be obviously relevant to all sorts of sports like baseball and golf or fencing, but in general we may want to look at how long objects rotate as they are spun about different axes along their bodies. So let's take again an example of an object that has uniform mass, at least in this case along the length of the stick, and it has a length L. And we'll approach this the same way by looking at how we can break up this piece into little pieces and add them up together. Now in this case we can actually go right back to our definition for the moment of inertia as the sum of the little mass pieces times their distance from the rotation axis, the perpendicular distance from the rotation axis. And in this case, let's look at the mass here as a combination of a density times a little bit of length along that stick. Now in this case, we're really looking at a one-dimensional object, and so the density, the mass density, or the linear mass density on this object is just mass divided by the length of the stick. And then if we're interested in looking at just one little piece of mass here, let's call that delta r for a little piece outwards. That means that little piece of mass is just that density times that delta r term. Okay, so we get out mass over length times a sum of ri squared times delta r, and you see again we have something that we can turn into an integral very easily. This is going to be the integral of ri, and actually we don't need the I anymore because we're turning it in the integral. We're getting rid of the summation. So it's just the integral of r squared dr, and we're doing this integral about the entire length of the stick, but we're really starting from the sort of the minus L over 2 to L over 2. We're going from one end to the other one with the origin at the middle. So this is really minus L over 2 to L over 2 as our integration limits. And again, this is a nice easy integral to do. This is 1/3 times r cubed evaluated at the two endpoints. So that means that it's L cubed over 8 minus a minus L cubed over 8. So that's plus L cubed over 8. So this integral is just equal to 1/12 times L cubed. And so we get out our final moment of inertia for our stick is just 1/12 times L cubed times mass over L, so that's 1/12 times mass times length squared. Okay, so again we approach it from the same approach by breaking up our object into little pieces and turning the summation into a very simple integral. Now that's the case of twirling something like a marker along its center of mass. We can also look at what happens if we want to twirl it around, say, one endpoint. Again, that might be something that's relevant for baseball or golf, where you're swinging a club along one endpoint of the stick. Well, in this case, we don't have to go back and redo our integrals because we have this parallel axis theorem, whereas if we want to look at the rotation of this object about an end as opposed to the middle, this is looking at a parallel rotation axis to our original rotation axis. So all we have to do is add in the moment of inertia term that comes from sliding it over by L over 2. So the new moment of inertia, and we'll call this the end moment of inertia, is just equal to our center of mass moment of inertia plus the mass of the object times this distance squared, so L over 2 quantity squared. So that's 1/12 ml squared plus 1/4 ml squared. And that's just 3/12, so that becomes 4/12, and we end up with an expression of 1/3 ml squared for the moment of inertia of a stick swung by the end point. So you can see all of these expressions are quite easy to derive once you use the rules for calculating moment inertia. And those rules include the parallel axis theorem, but also making sure that you add these pieces together. And then once you know the moment inertia of one kind of piece, you can always build up other more complicated shapes. So we could take this stick and add a ball to it or a hoop and calculate the moment inertia by just adding those together. You can see there's many ways of building up much more complex objects based on just these simple shapes that we've done here.